recent activity in the field of spintronics, and I will try to correlate our research focus with the theme of the conference, where we are using our scientific awareness in the research that can benefit the society. And we are living in the quantum era, quantum world. So we will our research is focused on some of the quantum materials. So I will discuss some of those results here. So this is the overview of outline of my presentation today. First, I will give the overview of the research activities that we are involved in our group at IIT Roper. So I am leading the group of quantum spintronics at Department of Physics IIT Roper, where we focus on spintronic devices and we develop new materials that can improve the performance of the existing spintronic devices. Since the audience is very broad, I will try to first give the brief introduction about the device where we focus. So, and after giving the introduction about the device like spin-hole and oscillators, then I will talk briefly why we are interested in these type of devices and how can we improve the performance of the existing devices using the quantum materials. So we use our understanding of the quantum materials to benefit the society. How can we benefit the society using the quantum materials in the existing devices? That is the main focus of my talk today. Where I will focus first on the devices that is all their oscillators. We make use of the magnetic field metals. So, and later in my presentation I will electron charge. But in 1965, the scientist Gordon Moore gave a law, Moore's law. So according to the Moore's law, every 2 years, the number of transistors are doubling on a microchip. So since 65 until now, we have reached the limits of the miniaturization. So we cannot accommodate more devices on a microchip. So then what we can do next? Because we already reached the limits of miniaturization, we cannot go beyond that. Like in transistors, as my colleague explained that we can use different type of materials because the size of the transistors are already in the nanoscale range. So if we further try to reduce the scale of the devices, then we reach in the quantum limit. Like then the physics laws are not valid. So we are already saturating in that domain. So we need new physics, new directions. So here comes the spintronics. In spintronics, we not only use the electron charge, we try to use the electron spin as well. As you all, I hope all of you know that in atom we have electrons, and the electrons have both spin. Electron is revolving around the nucleus, that's called orbital motion, and the electron is also spinning at its own axis, that's called spin angular momentum. So in spintronics, we try to use the spin property of the electron together with the electron charge. And using the spin property of the electron, what we try to do, we try to reduce the power consumption of the devices and increase the operating frequency. And if we talk about the magnetic storage devices, we try to increase the storage density while keeping the energy consumption low. So in that direction, we look for the materials for spintronic devices. Some of the focused areas in our group is, as you can see here, we try to develop highly spin polarized materials. In highly spin polarized materials, what we do, we look for the materials which have only presence of one type of carriers are present at the Fermi level. Because of that, we have fully spin polarized band structure. Like only upspin or downspin electrons are present at the Fermi level. Because of that property, we can have the device improvement in the devices like magnetic tunnel junctions. So that and we also focus on magnetic tunnel junctions where we have two magnetic layers parallel to each other. So we try to manipulate the magnetization of one of those layers while keeping the other layer fixed, and then we measure what is the change in the resistance of that device. So these are some focus areas in magnetic memory applications. We also have interest in materials, especially in quantum materials like two-dimensional materials. We try to use two-dimensional materials for spin-orbit torque properties. Since they have a strong spin-orbit coupling, we use those materials to get the spin-orbit torque, especially the unconventional torque. We call it unconventional torque because when we apply a charge current in x direction, we expect that the spin polarization will be in y direction and spin are propagated in z direction. But in unconventional spin orbiter, both the spin propagation and the spin polarization direction are parallel, which is not possible with the physics alone. So that's why it is called unconventional spin orbiter, which cannot be explained with the fundamental laws of physics. And then we use van der Waals magnets to get better performance of magnetic materials. So today I will focus on specifically this kind of devices, spin Hall nano oscillators. So I will first introduce what is spin Hall nano oscillators. So spin Hall nano oscillator was first introduced in 2003 by a Cornell group from Cornell University. Daniel Ross group first proposed this kind of devices. As you can see here, we have two magnetic layers. One is capital N and this M. So when you apply a charge current in this layer, and because of the spin polarization of that layer, as I hope all of you know that the ferromagnets have spin polarization because of the exchange interaction, and because of that spin polarization, the charge current which will pass through this magnetic layer gets spin polarized, and it passes through the normal metal, and then when it enters this layer, the spin current after entering in this layer exerts a torque on the magnetization of this layer, and because of that we see the magnetization dynamics. And we are interested in the dynamics of that material, especially in the microwave region. Okay. So this was a very complicated device where we need to fabricate devices in the nanoscale region. And thanks to my colleague Vijay, who explained very nicely what is nanoscale. So you can now imagine the scale of the device. It is in 10 to 500 nanometers, which is not easy to fabricate. And especially if you have a vertical structure. So if we have a horizontal structure single layer, it is easy to fabricate. If you were trying to make a structure using this kind of pillar, it is not easy. You see the dimensions of the devices. Then a simpler device was proposed by Day-2 et al. Rather than having this vertical structure in this kind of oscillators, which we call spin Hall nano oscillators, we have only two layers. One magnetic layer, here we are using permalloy, and other non-magnetic layer, which is platinum. So the benefit of using this kind of devices over this is that it is simple binary devices, and you just need to pass the current in the platinum layer, and then platinum layer because of this strong spin orbital will exert a will generate spin current that will pass through the magnetic layer, and that spin current will exert then torque on the magnetization of that layer, and we see the magnetization dynamics and the macromagnetic simulations from this work can be seen here. This is the intensity of the magnetization auto oscillations. So in the next slide, I will try to explain more deeply what's magnetization auto oscillations, how we see the dynamics of the magnetization layer. But before going to that, I will explain why we are interested in this kind of devices. Why we do need to work in spin Hall nano oscillators. Because this kind of devices have various applications. These devices can be used in wireless communications. We use these devices for microwave assisted hard drives, and in our previous group we also use this kind of devices for neuromorphic computing. So we try to mimic the computing of human brain. Like in human brain we have neurons and synapses. So in our devices we try to mimic the computing like human brain. So we try to make our devices, which is a nano oscillator, work as a neuron, and then they interact with each other due to the spin waves, and those spin waves are generated when the magnetizations are oscillating. So these kind of devices are then used for the neuromorphic computing, which is unconventional computing, and the group from France, they use these kind of oscillators for the vowel recognition. They apply a microwave signal to one of the reference devices, and then they try to analyze whether the device are able to recognize the signal they have given as an input. So using the four oscillators in series, they were able to demonstrate that using those devices they can perform the vocal recognition. So now I come back to spin Hall nano oscillator again to explain how it works. So as I said, when we apply the charge current in this non-magnetic layer, which is platinum here, when we apply the charge current, as you say here in this geometry, the charge current is applied in this y direction here. So when we apply the charge current, because of the strong spin orbit coupling in this material, we will see a separation in the spins, which will be in opposite in the direction orthogonal to the propagation of the charge current, and the spins are flowing in the perpendicular direction to that y. So we will see the spins are oriented in x direction and they are propagating in that direction. So because of this spins, we have torque in this magnetic layer. When these spins are entering this magnetic layer from this electron layer, they exert torque on this magnetization layer. How then this torque helps us to get the magnetization dynamics? We will see here. So when we have a magnet, we place that magnet in magnetic field. When the magnet is placed in the magnetic field, what we will see, once we apply the magnetic field to a magnet, the magnet will start, magnetization will start processing around the magnetic field like this. We have a magnetic field vector and we have magnetization. So when the magnetization vector will start processing and it will slowly damp. So that is called normal precession. I hope all of you have heard. So the magnetization will slowly damp. It is not stable. So to make magnetization stable, we need to apply some anti-damping like torque. As you see here, when the magnetization starts precessing, it slowly damped away. And after some time, it will align in the direction of applied magnetic field. To compensate this anti-damping like torque, which is causing the damping in the magnetization oscillation, we need to apply anti-damping like torque. So that we can compensate this damping like torque with this anti-damping like torque. That we apply with the application of charge current. So when we apply the charge current, we can make a balance between damping like torque and anti-damping like torque. As you can see in this relation, then we can sustain a situation where magnetization is processing around the applied magnetic field in a steady mode, like it can process for a very longer time, so infinite time. So if we can sustain a anti-damping like torque that can compensate a damping like torque, we can have microwave signals generated with this kind of devices. So, but there are some challenges in these devices because the magnet we are using in these devices are normal ferromagnets, and the materials for the spin orbit torque we are using platinum or some other heavy metals. So the challenge remains how to improve the operating frequency, because the current operating frequency of the devices are in the range of like 2 to 10 gigahertz. But if we are looking for a real application, like I said in the introduction, these devices can be used for neuromorphic computing. So if we want to use these devices for neuromorphic computing, which is like human brain computing, then we need devices that can work in the terahertz range, like the frequencies larger than or near to the 100 gigahertz. Or we need to reduce the power consumption. We need our devices to work at very low current densities, so that we can reduce the power consumption, because these devices at present consume a lot of power. So we try to minimize the power consumption and improve the operating frequency of the devices. So in that direction, we look for new materials which can help us to achieve that goal of high frequency operation and reducing the power consumption. So here comes quantum materials. So, and I don't need to go much deep into the quantum materials, which was very nicely explained by Dr. Vivek and Dr. Vijay. So we are interested in materials, quantum materials like wild semimetals. These are the materials which in the beginning has like degeneracy in the energy. So to break the degeneration in the energy, we have two wild points here. So now if we want to break the degeneration, we need to remove the degeneration in the energy, we need to break the symmetry, either the time reversal symmetry or the inversion symmetry. After we break one of the symmetries, we can make two wild nodes separated in K space, and then we can have a system like this. So we are interested in materials like this where we have wild nodes, and because of these wild nodes we can see the topological features of the material. So I will not go much details into that, but these are the materials which we are interested. These materials can improve the device performance which we are interested in, as they have strong spin orbit torque and some of them show very interesting magnetic properties. So These are some of the examples in the literature which show very strong spin orbit torque, like this paper from Max Planck Institute in 2016. They reported that the material tantalum arsenide here, shown here, it's near to the wire node. We can see strong spin Hall conductivity. So this shows very strong spin orbit conductivity near to the wire node. And this material, which we are interested in our experimental work, this was experimentally grown first in Princeton University in 2019. It is a full use alloy, cobalt to manganese gallium. And this material also shows interesting topological features. So we are interested in materials like this. We want to use these materials to our devices, but we cannot use them in bulk form. First, we need to get thin films of these devices, because our devices scales are in nanometer scale. Like first, we need to grow the films in nanometer range, which is quite small. Again, thanks to Vijay, very nice explanation of the nanometer range. So we first grow thin films of this material. So in bulk form, this material, cobalt to manganese gallium, it has a very excellent properties because of its topological features like wire nodes, other surface states. But the challenge remains, can we sustain those properties in thin film form? So we started from slightly thicker thin films and try to see whether we can sustain those properties in thin form, which is different from what Vijay explained, that when we change from bulk to nano, the properties of the material change. But we are interested in the material properties sustained at the nanometer scale, like the properties what we have at the bulk range, we want those properties to sustain at the nanometer scale. Then only we can use this type of materials in the devices. If we lose the properties what this material show in the bulk form, it is not useful for us. So we first try to grow this material in thick film form, like in the 10, 20 and 10. I am calling it thick because for us any thickness range more than 10 nanometer is thick range. So we first grow the thickness more than 10 nanometer, and here I show the crystal structure of this material. We perform X-ray diffraction measurement, and then we confirm our thin films are nicely single crystalline thin films, similar to the bulk materials. As you can see here, here we also do 5 scan of our thin films to confirm the symmetry of our thin films. As you can see, very nice 4-fold symmetry. We have cubic crystal. So for a cubic crystal, we perform the 5 scan for fundamental peak 110, and then we can see very nice 4-fold rotation symmetry, which again confirms that the quality of the thin film. We then also interested in the material properties, like whether there is any disorder between the antisides, like when we grow thin films. We also expect that the atoms are not occupied at their respective atomic sites. It is also possible that the cobalt can go to the gallium side and gallium can go to the cobalt side. And it can also happen that manganese occupied the cobalt side and cobalt occupied the manganese side. So we also studied whether such kind of antiside disorder is present in our thin films. That we confirm using XRD measurements. And you see here the comparison between our experimental investigation and the theory. So experimentally, if it is a perfect crystal, what we expect, both V2 ordering, which is the ordering between cobalt and gallium. In V2 ordering, we try to summarize that if there is any ordering, any disorder between cobalt and gallium. And here, as you can see here, see that we have almost perfect V2 ordering. So there is no disorder between cobalt and gallium sites. Then we are interested in whether there is any disorder between manganese and cobalt sites. That we study with L2 disorder. So L2 disorder parameter tells us whether we have any antiside disorder between cobalt and manganese. And here, as you can see, you find some antiside disorder between cobalt and manganese. But still, it's better than the previous reports from other groups. Then we do further studies. What we do for the magnetizing dynamics before making the nanoscale devices. What we did, we have the phonomagnetic resonance measurement setup here, where you can see the coplanar waveguide. We have microwave signal on this conducting line. We place our thin films over this conducting line, and then we try to study the magnetization dynamics of our thin films. And I have shown the data for 15 gigahertz of frequency. When we apply 15 gigahertz of frequency, and while we are switching the magnetic field, we look for the resonance condition. Okay, so the data for 15 gigahertz is shown here. So whenever there is a resonance between this microwave signal and the rotational frequency of the magnetization, we see this kind of field. So we perform these parametric resonance measurements in frequency range of 2 to 40 gigahertz, and the results are summarized here. As you can see here from our analysis, we see very low magnetic damping constant, which is very important factor when we consider the power consumption, because as I explained in the beginning, if the magnetic damping is higher, magnetization will try to align in the direction of magnetization very quickly. We need more current to balance the anti-damping electrode. If the damping parameter, which I defined with the alpha, so this is equivalent to the current we need to compensate that. If this parameter is low, then we need low currents to balance the anti-damping electrode, which is causing the magnetization to align in the direction of applied magnetic field. Then we perform the transport measurement on these films, and as you can see here, we obtain very nice results. There I will not go much into the deep of these results, but I just want to make one statement. The values we got here is comparable to the bulk values, which again proves that the quality of our films is quite nice. I think so far so good. So until now we just confirm whether the material which we are growing having the properties which this material have in the bulk form. So from the measurement so far, we can say that we are able to sustain the properties of this material in the films of 20 and 30 nanometer. So now we were sure until this point that yeah, this material is good. We can use this material for the devices like oscillators. So before making the oscillators, we were also interested in making devices for the spin orbit torque. So we measure to measure the spin orbit torque. So to measure the spin orbit torque, we make the devices that can measure the spin orbit torque, and we make devices like spin Hall oscillators or microchips that we can use for the magnetization auto oscillation measurement. And this was the tool which we used for the device fabrication, and that tool was in Sweden that I used during my marriage stay in Sweden. So we make devices like this. Here you can see nice constructions made of 50 nanometer scale. This construction is 50 nanometer, and these lines are contact pads. These pads we use to measure the sample. These are slightly bigger than the devices, so we cannot make contact to the devices if the contacts are so small. So these are used for the contact, and the devices are here. The group scale of the device is here. This is the atomic force microscopy image of this SSNO device. We have also devices like this, microchips and hall bars. These microchips and hall bars we use to estimate the spin orbit torque efficiency. And as I said before, spin orbit torque efficiency of the material is important if we want to reduce the power consumption of the devices. So before measuring the spin orbit torque, we first measure the anisotropic magnetoresistance, because it's an essential property that we require before getting any spin torque parametric resonance signal. And we can see very nice anisotropic magnetoresistance for our samples. Then we use our hall bar devices, and the device geometry and the measurement setup is shown here. So we measure the first harmonics and second harmonics of the hall voltage, and then we use the first and second harmonics of the hall voltage to estimate the spin orbit torque efficiency. I will not go again much technical details of the measurement. If you have interest, I can answer your queries. But I want to say that the damping like torque efficiency which we obtained from our measurements is quite high, 0.82, which is almost order of magnitude higher than the previous values if we consider the other magnetic materials like other topological materials. So it was very nice. We were very excited because we can see the spin orbit torque and magnetism in a single layer. So then we further try to reproduce the spin orbit torque efficiencies of our material. We then make then we have microchips here, and the microchips were used to measure the spin dot paramagnetic resonance spectrum. Measurement setup is there. Again, I just want to focus on the number, not on the technical details. So using this technique also, we obtain very high value of spin Hall conductivity, which is reasonably comparable to what we obtain using the first and second harmonics of the Hall measurement. So we then confirm that the spin orbit torque efficiency in this material is quite high, that we can use to get our devices like small and oscillators that can operate at low temperature, and possibly using the topological materials we can also try to push the operating frequency of the oscillator. So for the spin orbit torque, since the value was very high, so we want to confirm using theory also. Then we took help from our colleagues in Japan, National Institute of Material Science. Then they performed calculations for the spin Hall conductivity, and the calculations are shown here. And we make a comparison of our work with the previous works, and you can see the values of the spin Hall conductivity is very high as compared to the previous reports on other paramagnetic materials. After that, we make the devices called oscillators. As I said before, we are interested in oscillators and how these oscillators works with this material. And the image of our devices you can see here. We use micro focus billion light spectroscopy, which is a direct optic technique which apply a laser pulse to our sample surface. As you see here, we have in this schematic, you can see here we have our devices here. So on the nano constriction region here, we apply a probing laser. Okay, when we apply a probing laser, when the laser pulse falls on the material, it can interact with the material in different ways. It can interact with the phonons of the materials or the magnons of the material. Depending on what is the reaction of this laser with the material, we can say that what will be the outcome. Since this material is magnetic material, we can expect that the laser will interact with magnons. So what will happen when we apply this probe laser incident photon to our material? It can either create a particle which is a Stokes-like event, or either eliminate a particle like anti-Stokes-like event. So what we see, we have a reference laser peak, we know the frequency of that peak, and then we see the shift in the peak of the reference signal. Like if we apply some reference signal in some frequency range, we see with another probe what is the shift in the energy of the applied laser. Depending on that shift, we see either Stokes-like event or anti-Stokes-like event. So with this kind of measurement, we try to study the magnetization dynamics, because this shows the spin wave. And as you can see here, we were able to see the magnetization auto-oscillations. This is the billion light spectroscopy count. So we can see the magnetization auto-oscillations at very low current densities. For this sample, we were able to see the magnetization auto-oscillations at very low current densities. The current density, if we compare with the devices, as I said before, the existing magnetic materials, the value we got here is almost 5 factor lower than the previous values. So with this material, we were able to reduce the power consumption of the spin Hall laser oscillator by 5 times. I think this is very good news, considering how we can use the quantum materials for the benefit of society. So whenever we are doing any research in all of these devices which I introduced in the beginning, we always look at what we can do for the society. If we are working on some device, like we look for the applications first. If we don't find any suitable application, we try to drop the idea of working on that device. Okay, so with that device, I think we can make a very good contribution to the future technologies based on the spin Hall oscillators. The power consumption reduced by 5 factors with this type of oscillators. This was good. So now I want to touch upon some different topics in next 10 to 15 minutes. So there we use a different type of material called compensating ferrimagnet. This type of material we have used because we are interested in high frequency operation. As I said, our aim is twofold. We try to improve the operating frequency of the oscillator and try to reduce the power consumption. So in the first aspect, using the magnetic wire semi-metal, we were able to reduce the power consumption, but we were not able to improve the operating frequency. So now using this type of compensated ferrimagnet, we try to improve the operating frequency of the oscillator. So since compensated ferrimagnets have two sublattices, So now I will introduce first what is compensated ferromagnet. So if you have done the course of condensed matter physics, you might have been gone through the compensated ferromagnet. So I will go slightly ahead of ferromagnet. In ferromagnets, you know we have two magnetic sublattices that we can say M1 and M2. So the net magnetization is M because we have unequal sublattices in compensated ferromagnets, which is different from antiferromagnets. If you talk about antiferromagnets, we have two sublattices. They are equal and opposite, so the net magnetization is 0. But in ferromagnets, we have net magnetization non-varying because sublattices are unequal, so we remain with some net magnetization value. And that net magnetization value, which is remaining in compensated ferromagnets, that will give us advantage over antiferromagnets. Since last 10 years, antiferromagnets are very interesting to the researchers working on ultra-fast dynamics devices. But there is a challenge in antiferromagnets. In antiferromagnets, as I said, the net magnetization is 0. So it is very difficult to measure the signal. Like if you are working on a device based on antiferromagnets, if the magnetization is 0, it is very difficult to detect that signal. So signal is almost 0. So we cannot detect that signal. So to detect the signal while sustaining the dynamics as close to the antiferromagnets, these materials are a very prospective candidate. So as we change the temperature in these type of materials, the sublattice magnetization change. They have very interesting property in sublattice magnetization. At some point at temperature, there will be a situation that the two magnetic sublattices will be equal and we will get a net magnetization equal to 0. So we are interested in temperature range where we can work around this magnetic compensation point. The net magnetization is almost 0, but it's not 0. We are going to work either left hand side or right hand side of this point, so that we have some net magnetization, but the dynamics are close to the ultra fast because of almost cancellation. Because we want net angular momentum to compensate, which will compensate at this magnetic angular momentum compensation point. So at this point, when they are equal, this is 0. So we look for the points where this is 0. So we are interested in near to this, where the net angular momentum is 0, but there is non-vanishing net magnetization. So this kind of point where the two magnetic sublattice is almost 0, but not cancelling, rather than changing the temperature, it can also be achieved by tuning the composition. If we have some material, let's say if we make alloy, like cobalt gadolinium, if we tune the composition, we can get a composition which is near to the angular compensation point at room temperature. Like the angular compensation point of some composition is near to the room temperature, then we can work on the room temperature. What we look for the device is the materials that can work at the room temperature. So we can choose this kind of property with the temperature also, not only with good composition also. So there are two ways, either changing the temperature or either changing the composition of the system, we can arrive at this point. So we are interested in this point. So looking at this, we selected a material called gadolinium cobalt, and this was the system which we used to make the thin film of the devices. Ultra high vacuum backdoor sputtering system. We have two ultra high vacuum chambers here. The 8 targets are here. We can grow 8 different kind of materials here and 7 different type of material in this chamber. So the total combination we have in this chamber is 15 different type of materials we can grow at one point if we want. So to grow gadolinium cobalt thin films, what we use co-sputtering of gadolinium and cobalt targets. We sputter together from cobalt and gadolinium and then try to get the different compositions of gadolinium cobalt thin films. And we initially choose the composition of the thin film 8 nanometer. Okay. So after drawing these 8 nanometer thin films on high resistance silicon substrate, so I have not introduced why we are using high resistance silicon, but let me touch upon briefly. We are using silicon here because we want to make our devices compatible with the existing CMOS technology. Okay, for that silicon is prepared. And then after making these thin films, we use our setup for parametric resonance. We place our thin films over it and then measure the dynamics. And the results of the magnetization dynamics can be seen here. So we obtain almost magnetization compensation near to this 25% composition of gadolinium. As you can see here, effective magnetization of the material is 0 at this point, and the magnetic damping constant is also minimum around this point. So with our paramagnetic resonance measurement characterization, we confirm that we were able to get the composition near to the angular compensation point, and that was very interesting if we are looking for a high frequency spin Hall line oscillator using these devices. Okay, after that we again go for different compositions. Then the previous results were on one composition. Then we choose the composition of our system. You see here the different compositions. So different compositions, you can see the final results here. Again, near to the 25% of gadolinium, we have minimum in saturation magnetization and effective magnetization. So this again confirms that near to the 25% of gadolinium percentage, we have really compensated ferromagnets, where we have almost vanishing net magnetization. So once we confirm that this composition around 25% is nearly vanishing, so then we choose around 3-4 different compositions near to this point to make the devices. So far we have not made any devices. That measurements were performed on thin films that were grown on a large area like 10 by 10 mm square. Then after this, once we confirm that our thin films of high quality and the presence of angular compensation point, we again made the devices like microchips or rectangular chips of the samples here shown in this schematic, and we use this kind of setup to measure again the spin orbit torque of our devices. So the results of the ST measurements can be seen here. So for these samples also, we see very interesting properties. Like for the different composition of the cobalt, gadolinium cobalt, you will see the different amplitude of the spin orbit torque efficiency. For 22% of gadolinium, we have positive spin Hall effect. For 23.4% of gadolinium, we have a negative spin Hall effect. So we see a transition in spin Hall conductivity when we change the composition of gadolinium cobalt, which is also very interesting for our application. So then we measure then we fabricate spin Hall line oscillators and measure those devices again using the same setup which previously I explained the optical measurement, but this time we did the electrical characterization. So this time we have not used any laser. So we use the electrical characterization setup where we have a spectrum analyzer that can analyze the signal in the frequency range of 2 to 44 GHz. So I will not go into the details of the analysis. So we analyze how the magnetization is processing when we apply the current. In this kind of sample where we have platinum and gadolinium cobalt, when we apply the charge current in platinum, how the dynamics in gadolinium cobalt is happening. We measure that using this setup where we have spectrum analyzer. And as you can see here, we can see the magnetization of oscillations in negative polarity of the current for both the compositions. This is different from what we observed in spin orbit torque efficiency. In spin orbit torque efficiency, we see a sign reversal in spin orbit torque efficiency for these compositions, but the magnetization of oscillations we get in the same amplitude of the current. This is quite surprising to us. So then we again use laser-based setup to measure the magnetization of oscillations. And with this setup, we also got the magnetization of oscillations for this sample. But the interesting thing comes here in this image. As you see here, the applied magnetic field is 0 here. We are not applying any magnetic field. Rather, we can see the magnetization of oscillations. So this was the first time when, I think to the best of our knowledge, it is not reported before that magnetization of oscillations can be achieved without any magnetic field. So it is required to get the magnetic field supply to the sample to get the magnetization of the oscillation. But in our sample, since these are different materials, compensated ferromagnets, we were able to get zero field magnetization of oscillations. We only applied the charge current. We did not apply any magnetic field, but still we can see our magnetization processing very steadily around the applied. So this was the temperature dependence or magnetic field dependence measurement of our devices. These measurements we perform because we want to see whether we can change the operating frequency of the oscillator paramagnetic mode or a exchange mode in our devices, we could not see any magnetized node oscillation as can be seen here or here. But what we see when we increase the temperature, this exchange mode, here you can see the line width of the mode is very large. You can see a line width in the range of 70 to 110 gigahertz, which is quite broad line width. But this is not as broad as reported in the previous one from this Demino et al. They reported, I think, almost for twice of our line width. So what we see here, when we change the temperature, this line width of the exchange mode is increasing. So what it says that this temperature was close to the angular compensation point, but when we increase the temperature, we are moving slightly away from the compensation point. When we move slightly away from the compensation point, as I said before, near to the compensation point, we have lowest frequency for the exchange mode, and then this frequency increases when we move away from this compensation point. So that we confirm in our devices. So here is the summary of my talk so far. I hope I could at least convey some of the message what I want to convey, but I will excuse me for a very advanced topic. I consider as it has international conference, I did not know the audience here, so the pitch of my presentation might be very high. So, but if you have any questions, please feel free to ask me.